So talking about economics, evaluating the economics of the transition isn't that simple. It has to be integrated approach. You can't just look at the pit or the underground mine in isolation. In the financial model needs to reflect both phases together. The standard tool is year-by-year cash flow modeling. This includes cost for building underground infrastructure, different production rates over time, and varying cost of open pit versus underground mining. The end goal is, of course, maximizing the project NPV. So to do that, project schedule is optimized. Open pit might run at higher output for a while, then taper off as the underground mine ramps up. The idea is to keep metal production steady because any downtime cuts into NPV due to discounting. Modern tools like mixed integer programming models helps with that. They show which ore blocks should be mined from the surface and which ones should be saved for underground. These models often reveal counterintuitive results, though. For instance, even if a block looks profitable in the pit shell, it might make more sense to mine it underground. That way, you can avoid the high cost of extra waste removal. In one case study, a sequential approach, which is pit followed by underground, delivered an NPV of $7.51 billion, with an optimal transition depth of around 887 meters, better than going fully open pit to the same depth. Another study found that optimizing the transition point boosted NPV by 2.06% compared to a non-optimized plan. That may not sound like much, but in large mine, 2% can mean hundreds of millions of dollars. I also want to mention that the transition to underground mining changes how we think about cutoff grades, which is the minimum grade that is still considered economic to mine. In the open pit mining, cutoff grades are usually lower, and that's because the cost to mine a ton of ore is relatively low. But as the pit gets deeper, costs go up, especially due to increased stripping. To stay profitable, the cutoff grade often rises towards the end of the pit's life. However, if an underground phase is planned, some of the deeper low-grade ore can still be reserved for later. Instead of pushing the pit deeper and spending more on stripping, mining can stop earlier and shift underground. The same material can then be mined more selectively and efficiently. This makes it critical to define both the final pit shell and the underground cutoff grade together. Underground mining usually costs more per ton, but it doesn't require stripping. So its cutoff grade is higher, for example, 1.5 grams per ton gold underground versus 0.5 gram per ton in the pit. During the transition, different cutoff grades are often used. High-grade ore may go straight to the plant, while the lower-grade ore is stockpiled until the final decision is made. Selectivity strategies change too. Open pit operations can tolerate small losses and dilution, typically 3 or 5%, but underground methods, especially like block caving, brings much higher dilution, often 10 to 20% of waste mixing in. This affects revenue projections. If you don't factor in lower grades from dilution, you just risk overestimating underground income. For example, in block caving, fragments of barren rock from the hanging wall can mix with the ore as it caves in. Each block must be evaluated not just by cost, but also by expected metal recovery after dilution and mining method. Some ore, like remnants in old pits or low-grade dumps, may not be even worth mining at all and are written off.